Recording in progress.
Hello, everyone. Today we are going through the DOE manual. It's volume 1 of 3. And this is the DOE Fundamentals Handbook of Thermodynamics, Heat Transfer, and Fluid Flow. Morning. Good morning, everyone. Guys, will
Recording in progress.
So good morning, everyone. Today we're going to cover the DOE Fundamentals Handbook. This book is Thermodynamics, Heat Transfer, and Fluid Flow. So we're going to go through 3 volumes in this class, and this is volume 1. So the objectives for this first volume is 1, to define the properties of specific volume, density, specific gravity and humidity, and to describe the classification of these thermodynamic properties, which is intensive and extensive properties, to define thermodynamic properties of temperature, pressure, and to describe measures of temperature like Fahrenheit, Celsius, Kelvin, and Rankine temperature scales, including absolute zero temperature, the freezing point of water and atmospheric pressure, the boiling point of water at atmospheric pressure, and to convert temperatures between these scales, which is Fahrenheit, Celsius, Kelvin, and these Rankine scales. Also to describe the relationship between absolute pressure, gauge pressure, and vacuum. And then to convert pressure between the following units. So you'll see pounds per square inch, inches of water, inches of mercury, millimeters of mercury, and microns of mercury. Then we're going to define heat, latent heat, sensible heat, and a unit used to measure heat. Also, we're going to define specific enthalpy, entropy. Describe the types of thermodynamics. So we're going to understand what an isolated system is, what a closed system is, what an open system is, and then we're going to define these thermodynamic systems. So thermodynamic surroundings, thermodynamic equilibrium, control volume, steady state. And then we're going to describe in this volume thermodynamic processes, like the thermodynamic process. What's a cyclic process? What's a reversible and irreversible process? What's an adiabatic process? What's an isentropic process, throttling process, polytropic process, and then distinguish between these intensive and extensive properties. And define saturation. Okay, what's a saturated solution? What's a supercooled liquid? What's a super heated vapor? What's the critical point? What's the triple point? Vapor pressure curve, quality, and moisture content. And then we're going to describe what these states of matter are, like the changes in states of these matters, such as sublimation, vaporization, condensation, and fusion. Okay. And then given this Mollier diagram and sufficient information, we should be able to determine any unknown properties for given a set of steam tables and sufficient information to indicate the state of the fluid, we should be able to determine any properties for a fluid, determine the change in enthalpy of a fluid as it passes through a system. And then we should be able to state the first law of thermodynamics, right? And then analyze an open system, including all energy transfer processes crossing the boundaries. Then we'll use the first law of thermodynamics to analyze cyclic processes for a thermodynamic system. Given this system, we're going to perform energy balances on all major components of the system. And then, given a heat exchanger, we're going to perform energy balance across two sides of the heat exchanger. Then we're going to identify the paths on this temperature entropy diagram, or T-S diagram, that represents thermodynamic processes occurring in a fluid system. Then we're going to go through and state the second law of thermodynamics, and then determine the maximum possible efficiency of the system. Given this thermodynamic system, we're going to conduct an analysis using the second law of thermodynamics. Given the thermodynamic system, we're going to describe the method used to determine maximum efficiency of a system, efficiency of components within a system. Then we're going to differentiate between the path for ideal processes and the path for processes that are real on this temperature, entropy, and enthalpy entropy diagrams. And given these T-S or H-S diagrams for a system, we're going to evaluate the system's efficiency and the component efficiencies. Then describe how individual factors affect the system or the component of efficiency. We're going to apply ideal gas laws to solve for unknown pressure, temperature, and volume. And then we're going to describe when a fluid may be considered to be incompressible. We're going to calculate the work done at constant pressure and constant volume processes, and then describe the effect of pressure changes on constant fluids. We're going to describe the effects of temperature changes on confined fluids. Okay, so there are 36 different objectives there. So follow along in your book or follow along here. So we're going to start by defining specific volume density, specific gravity, humidity, and then we're going to describe the classifications of these thermodynamic properties, which is intensive and extensive properties. So we first start out looking at the difference between mass and weight. So mass of a body is a measure of the amount of material present in that body. And the weight of a body is the force exerted by that body when the mass is accelerated in a gravitational field. So the difference between mass and weight is the fact that the weight is actually the mass times gravity. Okay, so mass and weight are related as shown in the equation below, where weight is equal to mg over gc. Weight is in pounds per force. Mass is in lbm, or pounds per mass. And then acceleration of gravity is a constant. So they give you 37.17 foot per second squared. And then the gravitational constant, which is GC, which you see at the bottom of the equation, is 32.17 lbm feet per lbf second squared. Okay, so you do get some constants here, and you do need to know what those are. All right, so anytime you see the variables G and C, you should already know what values to plug in. You're not going to look through the equation to figure those out. All right, so make sure that you highlight those because you're going to need them. So GC has the same numerical value as the acceleration of gravity at sea level, but is not the acceleration of gravity. Rather, it is a dimensional constant employed to facilitate the use of Newton's second law of motion with English system units. So you guys understand that pounds are the English system of units, okay? So they're not metric. The weight of a body is a force produced when a massive body is accelerated by a gravitational acceleration, and the mass of a certain body remains constant. So if I'm here, if I'm on the moon, my mass doesn't change, but the gravity does change, so my weight changes, okay? I'm still, all me is there, but my weight is going to change, okay? So the mass of a certain body, it remains constant even if the gravitational acceleration acting upon the body changes. That's what that statement means. That if I go, like if you see people who go to the moon, they're able to bounce around, and even when they're in spaceships, they're able to float around, okay? All of them is there, but their weight has changed. So that's what that statement means. So according to Newton's second law of motion, and here's another equation, force is equal to mass times acceleration, okay? Where A is acceleration. Gravity is another way of talking about acceleration, okay? So for example, on Earth, an object has a certain mass and a certain weight. The same object is placed in outer space, which is the example that I gave earlier. From the Earth's gravitational field, the mass is the same, right? All of it is still there, but it is now weightless. There's a weightless condition, and that is gravitational acceleration. Thus, the force is equal to 0. The English system uses lbf, that's pound force, okay, as the unit of weight. Knowing that the acceleration has units of foot per second squared, and using Newton's second law, we can determine that the units of mass are what? Pounds per force second squared per foot, okay? And so for simplification, 1 pound per force second squared per foot is called a slug. So all of that is called what? A slug. So the basic unit of mass in the English system is the slug. However, this slug is almost meaningless as a unit of measure, okay? You know, for the average person. So the unit of mass is generally pound mass, or lbf. So correct that in your notes, pound mass, lbf is pound mass. So in order to allow pound mass to be used as a unit of mass, we have to divide Newton's second law by this gravitational constant, which is GC. Okay, so I gave you the constant 32.17. Pound mass foot per pound per force second squared, and I said that's GC, or the gravitational constant. So we can substitute that with Newton's in Newton's law. So that would be the force is equal to mass times acceleration divided by this gravitational constant. So what they're doing here is they're going through what we call a derivation. They're deriving the equation that they previously gave you. Okay, so what they're doing is they're showing you how they came up with this. Okay, so they're showing you how they came up with this. So don't get caught up in all the steps of derivation, right? The important equation is the one that you can previously, right? They're just showing you the proof that this equation does represent how you determine weight. Okay, so don't get caught up in every step for a derivation. All right. So understand for this class that you're going to be given an example. You're going to be given the equation that goes with that question. You're going to define all the variables, and then you're going to solve for what's unknown. And so you're going to see that a few times. All right. So don't get caught up in all the different steps. So using the gravitational constant GC, and it adapts to Newton's second law, such that 1 pound per force is equal to 1 pound per mass, you know, on the Earth's surface. All right, so they're giving you a conversion factor here. So a pound per force is the same as a pound per mass on the surface of the Earth. And they give you a condition as to why they can give you that conversion factor. So it's important to note this relationship is only true on the surface of the Earth, where the acceleration due to gravity is 32.17 foot per second squared. However, because of all of our discussions are based on experiences and observations on Earth, we will be using the pound mass as the unit of mass, LBM. So when we're talking about weight, A is often written as G. As G. So in this case, acceleration is gravitational acceleration due to the Earth's gravitational field. So in other problems, they may give you all these different values for acceleration. But when we're talking about weight, we have to think about the gravity, okay, or the acceleration due to gravity, which is a constant. So please understand that whenever they're talking about weight, the value for G is 32.17 foot per second squared, okay? So this is a constant. That's only for weight. If they talk about any other force, then usually that A is supplied. Okay. Sometimes when they know that they've given you the constant already, they may not necessarily tell you because they're expecting you to understand that whenever you're talking about weight, anybody's weight, you have to include gravity. Okay? You have to use gravity. So using that equation 1, 2, prove that 1 pound per force is equal to 1 pound per mass on Earth. And so here we have a different, this derivation, right? So don't necessarily get caught up in all of the steps. I think that's one of the mistakes that I made when I started taking physics, is that I would get caught up in all the derivations. So for every problem, I would derive before I got to the equation and waste my time on the exam. So force is equal to mass times gravity. They're just showing you a solution here, and they're proving that that conversion factor is true here on Earth. Okay, so 1 pound per force, they've substituted in is equal to 1 pound per mass times 32.17 foot per second divided by that gravitational constant, which is 32.17 pound per mass foot over pound per force second squared. And so when they divide everything out, they wind up with 1 pound per force is equal to 1 pound per force. Okay, so all that they've done with all of these steps is just justify why they have this conversion factor. So if you get on the exam and you do all this, you're going to waste a lot of time. Well, you could have just said 1 pound per force is 1 pound per mass. Specific volume is the volume of a substance, or I'm sorry, the specific volume of a substance is the total volume of that substance divided by the total mass of that substance. So it's volume per unit mass. And a unit is cubic feet per pound mass. And so what they have in parentheses is how they write that unit. So you see this cubic feet or feet cubed divided by pound mass. Okay, that is specific volume. And then they give you an equation for determining specific volume. So specific volume is equal to the volume, remember they said the total volume, divided by the pound mass. And remember for mass, we're at, well, for this particular scenario, we are using the English system. Okay. So you're gonna have to get used to these units. So I always tell you guys about chemistry. Once they understand the physical world, then they mathematically define it. Okay. So they're telling you that specific volume is the volume per unit mass. And then they give you an equation which says specific volume is the volume per unit mass. Density of a substance is the total mass of the substance divided by the total volume occupied by that substance. So density is actually mass per unit volume. Density is actually mass per unit volume. And it has units of pound mass per cubic feet. Okay, and so they also give you another clue. They say that density of a substance is the reciprocal of the specific volume. And so that's where they have this mathematical definition. So density is equal to mass over volume, okay? Total mass over total volume. And that is the reciprocal. So that's why they're able to divide 1 over V. It's also the reciprocal of the specific volume. So if they ask you for a density and they only gave you a specific volume, then you would take the reciprocal of that value. That's what they're trying to tell you. So you would take that, you would take 1 divided by whatever that specific volume is, and that would give you the density. Okay. And so they're defining these variables here. So anytime you learn an equation, you need this bottom part as well. All right. So density, which is pound per mass per cubic foot. Mass is pound per mass. Volume is in feet cubed, right? Because we know that volume is a cubed unit. Volume is a cube. And specific volume, V, is cubic feet divided by pound per mass. Okay. So once you learn this equation up here, you have to write all of this down so that you know what every single variable in the equation is. You know, after you practice the problems enough, you'll remember what the variables mean. So specific gravity, that was another term that we said we would cover. This is the measure of relative density of a substance compared to the density of water at a standard temperature. I always talk about standard temperature and pressure. Why? Because we know that when the temperature changes, that impacts this particular characteristic of a fluid. So physicists use 39.2 Fahrenheit or 4 degrees Celsius as a standard, but engineers normally use 60 degrees Fahrenheit. The SI units, and we call it the International System of Units, the density of water is 1 gram per centimeter cubed. Okay, so we're using the English system, and that's why you see that the units are different. So your units for density were what? Pound per mass per, right, cubic foot. And in the SI system, the units are grams per centimeter cubed. So the density of water is 1 gram per centimeter cubed at standard temperature. And we're talking about SI units, okay? Now, for what I have seen, most of the time you guys use the English system, okay? So the specific gravity, which is dimensionless for a liquid, has the same numerical value as its density units, grams per centimeter cubed. Since the density of the fluid at a temperature, specific gravities must be determined and specified at particular. Okay. So that just means that that specific gravity, if you change the temperature, then that value is going to change. So they go ahead and fix it and say, look, we're talking about standard temperature. And they told you what engineers use, which is 60 degrees Fahrenheit. So engineers use 60 degrees Fahrenheit. Humidity is the amount of moisture, water vapor in the air. And it's expressed as absolute humidity or relative humidity. So absolute humidity is the mass of water vapor divided by a unit of volume of air. And that is in grams of water per cubic centimeter of air. So for absolute humidity, they gave you some units, okay, using the SI system. Relative humidity is the amount of water vapor present in the air divided by the maximum amount of air contained at that temperature. And relative humidity is expressed as a percentage. So relative humidity is 100% if the air is saturated with water vapor, and 0% if no water vapor is present at all. So humidity is expressed as, relative humidity is expressed as a percentage. So 100%, the air is saturated with water vapor, 0%, no water vapor. Intensive and extensive properties, they can be divided into 2 general classes. The intensive property, where the intensive property is independent of the amount of mass. And where the extensive property varies directly with mass. So intensive, mass independent, no matter what mass is. And you can still talk about its intensive properties. And extensive properties, they vary directly with mass. Thus, to quantify If matter in a given state is divided into two equal parts, each part will have the same value of the intensive property as the original and half the value of the extensive property. But what's really important when you talk about intensive properties is to understand that temperature, pressure, specific volume, and density are intensive properties. And mass and total volume are extensive properties. So the first part, intensive property, is independent of mass. Extensive property varies directly with mass. And then you will write temperature, pressure, specific volume, and density. Those are intensive properties. Mass and total volume, those are extensive. And so I like that this book has these summaries, okay? So you can go through the text and like, it'll flesh out what all of this is, but I like that these books have summaries for each chapter. Okay. So we've already defined what specific volume is. It's the total volume of substance divided by the total mass. We've already defined what density is. It's total mass divided by the total volume. We understand that specific gravity is a measure relative to the density of the substance as compared to the density of water at a standard temperature, and that humidity is the amount of moisture in the air, and it can be measured as absolute humidity. We talked about that, and then relative units, which is in percentages. Going back. Okay. So we can either say that absolute humidity is grams of water per cubic centimeters of air, or we can use relative humidity, which is in a percentage, okay? And then we said that intensive properties, they are independent of the amount of mass, and extensive properties, they are vary directly with the mass. And we said intensive properties are what? Temperature, pressure, specific volume, and we said density. Okay, those are intensive properties. The mass and total volume, those are extensive properties. And so that's what you need to write down up under those two sections. You need to write what the intensive properties were and what the extensive properties were. So for this first chapter, you should have highlighted formulas, what the variables mean, units, and then you should have gone to the summary to understand what the definitions are. That's how you study this. Any constants they gave you, like gravitational constants, you should have noted that. And any conversion factors, you should have notated those as well. Okay. Then go to the summary, and that's how you pull out your definitions. And to help you with the summary for intensive and extensive properties, you should have notated what they are. So if you make a crib sheet, the only thing you would add to this summary is not only what those intensive and extensive properties are, or any equations that you saw. All right, so we'll pause here so that you guys have the opportunity to do that. So we are back. So in this next chapter, we're talking about temperature and pressure measurements. So we're going to define these thermodynamic properties, which are temperature and pressure. And these are intensive or extensive properties. What kind of properties? Intensive or extensive?
You asking, are they?
Which one are they?
Oh.
Intensive or extensive?
Oh.
Back. Remember, they say temperature, pressure, specific volume, density, those are intensive. So we're going to describe Fahrenheit, Celsius, Kelvin, and the Rankine temperature scales, including what absolute zero is, the freezing point of water, atmospheric pressure, the boiling point of water, and atmospheric pressure. We're going to convert between those different scales, Celsius, Kelvin, and Rankine scales. Describe the relationship between absolute pressure, gauge pressure, and vacuum. And then convert pressures between the following units: pound per square inch, inches of water, inches of mercury, millimeters of mercury, and microns. So temperature is the measure of molecular activity of a substance. Temperature is also a measure of the kinetic energy, because the kinetic energy is the activity of the substance. The greater the movement of molecules, the higher the temperature. So it is a relative measure of how hot or cold a substance is, and it can be used to predict the direction of heat transfer. So two scales that are normally used for measurement purposes are Fahrenheit and Celsius scales, and these scales are based on a specific number of increments between the freezing point and the boiling point of water at standard atmospheric pressure. And so the Celsius scale, it has 100 units between the points, and Fahrenheit has 180 units between the points. And those 0 points are arbitrary. Those 0 points are arbitrary. The freezing point of water is selected as a 0 point for the Celsius scale. So the coldest temperature achievable for a mixture of ice and salt water is selected as the 0 point. So 0 degrees Fahrenheit, they're telling you how they come up with it. Okay. 0 degrees Fahrenheit, they're telling you how they come up with it. The temperature at which water boils is set as 100 on the Celsius scale. And the temperature at which water boils on the Fahrenheit scale is set up as 212. And so that's how they come up with this mathematical relationship between the two scales. That's the most important. So degrees Fahrenheit is equal to 32.0 plus 9/5 of whatever the Celsius temperature is. And for Celsius, that's equal to whatever the Fahrenheit temperature is minus 32 times 5/9. They're giving you these equations. Okay. So if you give them Celsius, you need to plug that value in here. Okay. If you're given Celsius, you need to plug that in here to find out what Fahrenheit is. And if you're given Fahrenheit and they want you to convert to Celsius, you need to plug that value in here. So they understood that it was necessary to define an absolute temperature scale having only positive values. So the absolute temperature scale corresponds to the Celsius scale. That corresponds to the Celsius scale is the Kelvin scale. Okay. And the absolute scale that corresponds to the Fahrenheit scale is the Rankine scale. And anytime you use those bars to make something absolute, you understand that those values need to be positive. Okay, so that comes from your understanding of mathematics. So the absolute temperature scale for Celsius is Kelvin. The absolute temperature scale for Fahrenheit is Rankine scale. And the 0 points on both of those scales represent the same physical state. And this is a state where you have no molecular motion of these individual atoms. So for those absolute temperature scales, what they try to do to set the value for 0 is look for a temperature where there was no molecular motion. So the relationship between absolute and relative temperature scales is the following. So they give you some equations. So the Rankine, remember, is the absolute scale for Fahrenheit. So Rankine is equal to whatever temperature Fahrenheit they give you plus 460. And Kelvin, the Kelvin scale or the Kelvin temperature is equal to the degrees Celsius plus 273. Okay, so if they give you a Fahrenheit and you want to find that same temperature on the Rankine scale, you need to take that Fahrenheit temperature and add 460. If you want to find Kelvin, they give you Celsius, you need to take that Celsius temperature, add 273, and that'll give you the temperature in Kelvin. And so here in this figure, they're trying to show you the comparison between the absolute scale for Fahrenheit, which is the Rankine system. So they start with Fahrenheit. They show you what the Rankine system does. Do you see at the bottom, there's a negative value? And you see that for the absolute scales, they make all these values positive. So whatever this negative value is on the Fahrenheit scale, it's negative 460, they set that at 0. That's the temperature at which there's no molecular motion. And then on the Celsius and Kelvin scale, you see they have a negative 273 under the Celsius. They set it to 0 to define the Kelvin scale. Okay, so they're giving you some of the theory as to why they say what they say. And it's all about molecular motion. And what's important for you guys is to understand how to apply it. So the conversion of one temperature scale to another is sometimes required at nuclear facilities, and the operator should be acquainted with how to, convert from one temperature scale to another. So what is the Rankine equivalent of 80 degrees Celsius? What is the Rankine equivalent? Well, in order to do this, the first thing you need to understand is what scales go together. So they added an additional step because you know that Fahrenheit and Rankine go together. See that? Remember, Fahrenheit and Rankine go together. Celsius and Kelvin go together. No, Fahrenheit. So in order to make all the values positive, they take that really low temperature that they discovered that there's no molecular motion that in the Fahrenheit scale, and they set it to 0 for the Rankine system. Right, you would have to convert. So if you have 1 Fahrenheit, you would add that, you would put that 1 right here and add 460, just like you said. See, you put that here, 1 degree Fahrenheit, and then you would add 460, and that would equal, okay, just like you said.
I just didn't know if it went.
So they just did experiments until they found, so they would take like a something that measures Fahrenheit, and they'd do experiments until they're like, okay, there's no molecular motion here. You know, even if they have to go to Antarctica and they'll find a place where there's no motion, the coldest temperature possible. And then they'll say, okay, when we measured it, it was 460. I mean, I'm not saying they went to Antarctica, you know, I'm saying that they find the coldest temperature, they measure it, and then set a scale, on another scale, they set it at 0. So here we know that Rankine and Fahrenheit, those two scales go together. So what's the Rankine equivalent of Celsius? We know that Rankine is not the absolute temperature scale for Celsius. So you got to find Fahrenheit first in order to use this equation. So this process is actually 2 steps. Okay. And so that's why the first thing they do is they take that Celsius value and they find the Fahrenheit. So 9/5 times that temperature, which is 80 plus 32, right? So they plugged in 80 in this equation. So degree Fahrenheit is equal to 9/5 times whatever that Celsius temperature given is plus 32. And they have to do that because there's no C in that Rankine equation. Okay, so they wind up with 176 Fahrenheit. Then they're gonna take that value and plug it in that Rankine scale equation. All right. So because they gave you this in Celsius, it's implied that you're gonna have to do 2 steps. All right, so they plug in that 176 plus 460, and they got 636 Rankine, degree Rankine. All right, so sometimes you need to like make sure that you write down what's given. You write down the equations. You understand what these variables mean so that you can solve the problem. And because they start out with Celsius versus Fahrenheit, that automatically let you know you had to do 2 steps. Okay, there's no C in this equation. So for your second example, same issue. Because Kelvin, the Kelvin equation doesn't have any Fahrenheit in it. So you got to be able to calculate a degree Celsius, because they start out giving you the question, what is the Kelvin equivalent of 80 degrees Fahrenheit? So they let you know that C is equal to 5/9 times F minus 32, degrees F minus 32. So 5/9 times 80 minus 32 gives you a Celsius temperature of 26.7. You're going to take this temperature in Celsius and you can find what Kelvin is. So Kelvin is equal to degrees Celsius plus 273. So now you add 273. So this problem is making you go through 2 steps. So this problem is making you go through 2 steps. So 26.7 plus 273 is equal to 299.7 degrees Kelvin. Pressure is a measure of the force exerted per unit area on the boundaries of a substance. And it's caused by the collision of the molecules of the substance with the boundaries of the system. So the molecules hit walls, they exert force and try to push the walls out. And the force from these collisions causes the pressure exerted by a system on its surroundings. So the pressure is measured in pounds per force per inches squared. And that's another way of saying PSI. So they give you these expanded units and then they give you PSI. Pressure scales, when pressure is measured relative to a perfect vacuum, it's called absolute pressure, SIA. Absolute pressure is PSIA. When measured relative to atmospheric pressure, 14 PSI, is called the gauge pressure. PSIG is gauge pressure. So the ladder pressure scale is developed because almost all pressure gauges register 0 when open to the atmosphere. And so these pressure gauges measure the difference between pressure of the fluid to which they are connected and then the surrounding air. So if the pressure is below that of the atmosphere, then we call it a vacuum. And a perfect vacuum corresponds to absolute 0 pressure. So all values of absolute pressure are positive because a negative value indicates that there will be some tension, which is impossible in any fluid. So gauge pressures are positive if they are above atmospheric pressures and negative if they are below atmospheric pressure. Okay, and so that's what you see. And so they give you these expanded equations. Okay. And so they give you these expanded equations. So absolute pressure is equal to pressure of the atmosphere plus pressure of the gauge. Or absolute pressure is equal to pressure of the atmosphere minus the pressure of the vacuum. So P, ATM is atmospheric pressure. And it's also called barometric pressure. P gauge is gauge pressure, and P vac is pressure in the vacuum. And these are helpful when understanding the idea of a gauge versus absolute pressure. This is page 10. And then they give you an example. So how deep can a diver descend into the ocean where the density is 64 pounds per mass, cubic feet per cubic feet, without damaging his watch, which will withstand the absolute pressure of 80 PSIA. The equation for pressure is density times height. Density. So when they ask you how deep the diver can descend, they're talking about the height. They ask you how deep can the diver descend, they're talking about the height. So they give you a value for the atmospheric pressure. They give you 14.7 psia. Absolute pressure is defined as 80 psia. Okay, and that comes from the question. 80 psia. It comes from the question. So the absolute pressure is equal to the atmospheric pressure plus the pressure to gauge. So they plug in for absolute pressure, 80 psi. That comes from the question. And that's equal to 14.7, which they give you as the atmospheric pressure. So they define that. Plus the pressure to gauge. They get P gauge by itself by subtracting 80 from 14.7, and it's what? 65.3 PSIG. Then they tell you here that the pressure to gauge, they go back to this equation up here, is equal to density times height, or rho times h. Right? Density, rho, height is h. Okay. Right. That's correct. So here they have your 65.3 p6 times 144 inches squared per foot squared. And they simplify that to equal 64 pound per mass per cubic feet times the height. Okay. And so height is equal to 65.3 times 144 divided by 64. So the height that diver can descend without breaking or damaging his watch is 146.9 feet. So that is a conversion factor, right? That is considered a conversion factor. This right here is considered a conversion factor. Yes. So in this case, it's going to be the same.
So no matter what,
Yes, right. So this is a conversion. Pressure relationship example, what's the absolute pressure at the bottom of a swimming pool that is 6 feet deep, that is filled with fresh water? They give you that value again for the atmospheric pressure, which is 14.7 psia. They go back and they say the equation that you need to use to solve this problem is absolute pressure is equal to atmospheric pressure plus gauge pressure. And then for gauge pressure, they substitute in that formula that comes from this other problem. Pressure of the gauge, they said, is equal to density times height. And so down here, they just do a substitution for the gauge pressure, it's density times height. So it's pressure of the atmosphere plus density times height. Okay, so they just substitute it in. So 14.7 is equal to 62.4 pounds per cubic foot times 6 feet. And then they give you that factor again, divided by 144 inches squared per foot squared. So give you that factor again, and you see it in the problem above. Okay, you see it in the first example. $62.4 pound mass per cubic foot. It's a density that they gave for a swimming pool. In the first one, we're talking about the ocean. The ocean has all this like salt and minerals. And that's a standard for the water that you have in a pool, which is not as dense as ocean.
I mean, it's constant, fresh water, salt water,
Okay.
but I just didn't know where the salt water is.
Yeah, this book assumes that yeah.
Okay.
So I'm trying to
Yeah, no, it's
Okay.
I'm just trying to figure out.
yeah. So you guys make sure you ask me because this book assumes that some of this stuff that so let me know if you don't get something. I have no problem with explaining it. They assume that you know certain conversion factors. They assume that you know certain constant value. So from this problem, there were some things that you already, some values that you already had to know. And you see that the only thing that that they gave you was how many feet deep in the pool. Okay. And so once you solve it, you have a pressure, an atmospheric pressure of 14.7. That side where you put in the density equation, it simplifies to 2.6. So the absolute pressure in the pool at 6 feet deep is 17.3 PSI. So in addition to pounds per square inch, pressure can be measured in reference to the force that exists in the column of fluid at a certain height. And so the most common of these is inches of water, inches of mercury, millimeters of mercury, and microns of mercury. And so they list the conversion factors for that below. So you need to know conversion factors. 14 psi 8 is 408 inches of water. 14 psi 8 is 29 inches of mercury. 1 inch of mercury is 25.4 millimeters of mercury. And a millimeter of mercury is 10 to the third microns of mercury. So these are some conversion factors that they give you. So for the summary, like I said, I like to use these so that you understand like some of the definitions. You understand some of the important equations for the chapter. And, you know, here I would write down some other conversion factors that you learned, you know, those conversion factors for the different types of pressure. See that? So I would put some of those in, and some of those other constants they assume that you knew, I would put those in too. So I will pause so that you can finish making your note. And also I would put in P gauge, I would put in is rho times H, so that you knew that they substitute sometimes density times height for the gauge pressure. So I would put that in too. That P gauge is density times height.
Recording in progress.
So we are back, and I'm going to share my screen again. And we'll keep going through this volume 1. So this next section talks about energy, work, and heat. And we're going to define heat, latent heat, sensible heat, and the units measured, units to measure heat, and then define specific enthalpy and entropy. So specific enthalpy is H and entropy is S, usually S. So energy is the capacity to do work or produce heat. Energy is defined as the capacity of a system to do work or produce heat. And potential energy is the energy of position or stored energy. Potential energy is the energy of position or stored energy. So the equation for potential energy is PE is equal to mgz divided by this gravitational constant. So potential energy is feet times pounds per force. M is defined as the mass, the pounds per mass. Z is defined as the height from the reference level. Above from reference level. And that height is in feet. We're using the English system. G is acceleration due to gravity in feet per second squared. And the gravitational constant is 32.17 foot-pound mass per foot per force second squared. Okay. So remember with these equations, you not only need the equation, but you also need to understand not only what these variables mean, but what units they're measured in. So that's what you need to know. So with these engineering calculations, the acceleration due to gravity is numerically equal to the gravitational constant, which is something that we defined earlier, which is 32.17. 32.17. Thus, the potential energy is in foot-pound force, and is numerically equal to the product of mass in pounds mass times height, which they use as Z for it. Okay. Now, how did they talk about height in the last chapter? When you talked about gauge pressure, how did they talk about height there? Right, they use the H. So they use the H in the last chapter to talk about height. Here they use a Z. And for enthalpy, they will use. So you have to keep all that. straight. In feet above some reference level. So here's the example problem. Determine the potential energy of 50-pound mass, right? Of water in a storage tank that's 100 feet above the ground. So the mass is 50 pounds, okay? They give you a height or a Z, which is 100 feet above ground. And so the equation for potential energy, which is defined earlier, is PE, potential energy is equal to mass times gravity times height divided by the gravitational constant. Then they show you the next one how they plugged in to solve. So they told you in this problem that the mass was 50 pounds. You see that here. This next value is a constant. This next value for gravity is a constant, so 32.17 foot per second squared. It's a constant that we gave earlier. And the Z, or the height in this case, is 100 feet, and they divide all of that by 32.17 foot pound per mass by foot pound, pound per force second squared. Okay. That's correct. So once you plug in and solve, you wound up with 5,000 foot pound per force. Right. That's right. And wound up with what? 50 times 100, which is, yeah, 5,000. So the potential energy is 5,000 feet or foot pounds per force. And then we talk about kinetic energy. So kinetic energy is the energy of motion. And in the English system units, it is defined as kinetic energy, or KE, is equal to mv. So you've seen this V a few times, right? Seen this V a few times, and it's not the same V. mv squared over 2g sub c, or the gravitational constant, where kinetic energy is foot pounds per force. Just like potential energy. M is the mass, pounds per mass. V actually is velocity, which is in feet per second. So you see a V for volume, total volume, specific volume, and also you see a V for velocity. So try not to get those mixed up. V is velocity, which is foot per second. And GC is still the gravitational constant, which is 32.17 foot pound per mass per pound force second squared. So if they ask you to determine the kinetic energy of a 7-pound mass of steam flowing through a pipe at a velocity of 100 feet per second, you know that you need to use the kinetic energy equation. Kinetic energy is equal to mv squared over 2gc. Here they tell you that mass is 7 pounds per mass. So you're gonna need to use that, and they tell you that the velocity is 100 feet per second. Okay, so you plug in what you see from this equation: the 7, which is your mass, and then your velocity, which is 100. So kinetic energy is equal to 7 pound per mass times 100 feet per second. You square that whole thing, divided by 2 times that constant, which is 32.17 foot pound per mass per pound force second squared. They went on ahead and squared that 100. That's how they have 10,000 foot squared second squared. So 7 times 10,000 divided by 64.34, because they multiplied 2 times 32.17. And the kinetic energy is 1,088 foot pound per force.
Second is about 100.
It's supposed to be 100 squared. So specific internal energy, potential, and kinetic energy are just macroscopic forms of energy. And they can be visualized in terms of position. As we said, that potential energy is position. It's also stored energy. And the velocity of these objects. So in addition to these macroscopic forms of energy, a substance possesses several microscopic forms of energy. So microscopic forms of energy include those through the rotation, vibration, translation, and interactions of molecules. So not only are they talking about the overall way that we talk about these forms of energy, but they're saying that these molecules, they actually rotate, they actually vibrate, translate, and interact with the substance. So none of these forms of energy can be measured or evaluated directly. Okay, yeah. So for a chemist, these types of motions, we actually use something that's called NMR. And NMR looks at the amount of hydrogens on the carbon that's next to the one that you get the peak for. And also it looks at rotation, vibration, and interactions of molecules. So we have to use NMR. That's not something that you guys use, okay? So it's not measured directly. It's measured. So you look at the protons on the carbon next to the one that actually have the peak for. And so techniques have been developed to evaluate the total sum of these microscopic forms of energy. So the microscopic forms of energy are collectively called internal energy. And it's represented by the symbol U. Right. So we have another variable. So you're going to have to make sure you keep these variables straight. Okay. So in engineering applications, the unit of internal energy is BTUs, which is also a unit of heat. BTUs is a unit for internal energy, and it's a unit for heat. So specific internal energy, lowercase u, of a substance is the internal energy per unit mass. And this is equal to the total internal energy, which is capital U, divided by the total mass. Okay, so here they have the lowercase u is equal to capital U divided by M, where the lowercase u is the specific internal energy, and this is BTU per pound mass. Capital U, which is the internal energy, which is BTU, and mass, which is in pound mass. So you have to keep those U's straight. Keep the U's straight. So if you determine the specific internal energy of a 12-pound mass of steam in a total, if the total internal energy is 23,000 BTU, then you're going to use the equation that was just given where a lowercase u is equal to capital U divided by M. U is in this problem 23,000 BTUs. You see that here. Divided by 12 pounds per mass, and you see that here for where they define what the specific internal energy is. And so U, lowercase u, is equal to 1,916.7 BTU per pound mass. Okay. And so you just have to keep those straight. All right, so they give you the total internal energy. They give you the specific, they give you the mass of the steam. They give you the total internal energy. And so you have to find the internal energy. So you have to keep those straight. They ask you for the specific internal energy. So that's your unknown. They give you the total internal energy and they give you the mass of the steam. So you have to keep those straight. So specific energy, in addition to internal energy, there's another form of energy that exists. And it's important when you understand energy transform within systems. This form of energy is called specific energy because it arises from pressure and volume of a fluid. It's numerically equal to PV, the product of pressure and volume. And because energy is defined as the capacity of the system to perform work, a system where pressure and volume are permitted to expand actually performs work on the surroundings. Therefore, the fluid under the pressure has a capacity to do work. In engineering applications, the units of PV energy is called flow energy. And the units of pressure times volume, which is pound force per square foot times cubic foot equals foot pounds per force. Specific energy of the substance is the PV energy per unit mass. And this is equal to the total PV divided by the total mass, or the product of pressure and specific volume. So in order to understand how all of this is derived, they kind of put it in paragraph, how they arrived at that. So P lowercase v is equal to PV over M, where P, or capital P, is the pressure, which is in pounds per force per foot squared. Capital V, which is volume, that is in cubic feet. Lowercase v, which is not the lowercase v we talked about kinetic energy. This is actually specific volume, which is a variable that's used in the earlier chapter. And this is cubic feet per pound mass. And this is also equal to V, the volume, divided by the mass, and the mass is in pound mass. Okay. So are these two P's the same? On both sides of the equation, are these two P's the same? Okay, so one is specific energy. Okay, so on this side, the left side is what we call specific energy. PV is equal to pressure over volume times, divided by mass. And so in order to determine the specific energy of a 15-pound per mass of steam at 1,000 PSI in a 18 cubic foot tank, you have to use that equation that was referred to earlier. Okay, so PV, we got a pressure there of 1,000 PSI. And they give you a conversion factor, which they're assuming that you know, the 144 inches squared per foot squared. And then times times the 18 cubic feet. Okay, times the 18 cubic feet, which is the volume of the tank, divided by the mass, which is 15 pounds per mass of steam, which is divided up here in this equation. So once they simplify it, the specific energy is equal to 172,800 pounds per force per pounds per mass. That is and then you have specific enthalpy. Now you've seen this H a few times, so you have to keep it straight. Seen the H for height. It was actually capital H. Then they talk about height, and they define it as Z. And so now they're using this H or lowercase h to talk about specific enthalpy. They have to keep you straight from here. So specific enthalpy is defined as lowercase h is equal to U plus PV, where U is the specific internal energy in BTU per pound mass of the system that you're studying. P is the pressure of the system, which is in pound per force divided by feet squared. And V is the specific volume, okay? And V is the specific volume. And that's in cubic feet per pound mass of the system. So enthalpy is used in connection with an open system problem in thermodynamics. Enthalpy is the property of the substance. And like pressure, temperature, and volume, it cannot be measured directly. Enthalpy cannot be measured directly. Normally, enthalpy of this substance is given with respect to some reference tables. So they usually, I don't know if you guys recall, but they usually have those tables with constants for H. They usually have those values like in tables. So they have constants for H. They have constants for S. They have constants for J. So it's usually in a reference table. So for example, specific enthalpy of water or steam is given in reference to that specific enthalpy of water is 0 at 0.1 degrees Celsius and normal atmospheric pressure. And so the absolute value of specific enthalpy is unknown, but that's not a problem. However, because it is the change in specific enthalpy that we look at, we're not looking at the absolute value. That is why it is not a problem. Okay, and so every time we see that delta, we understand that we're talking about final minus initial. So steam tables include values for enthalpy as part of the information that is tabulated. So it's not a problem because we use delta. Not a problem because we use delta. Delta is always indicative of final minus initial. Kinetic energy. So work. So we're going to talk about work. Kinetic energy, potential energy, internal energy, PV energy, are forms of energy that are properties of a system. And work is also a form of energy, but it's energy in transit. Work is not a property, it's a process. Work is not a property, it is a process done by or on a system. But that same system contains no work. This distinction between forms of energy that are properties of a system and forms of energy that are transferred to and from a system is important to understanding energy transfer. So work is a process done by a system. Work is not a property, it is a process. So work is defined for mechanical systems as the action of a force on an object through a distance, and it equals force times displacement. So through a distance, we call it displacement. Meaning, if I walk from this part of the desk to this part, and then I walk right back here, I have done absolutely no work. Because my displacement is zero. If I go from here to here and back, I have done zero work because displacement is zero. So work is in foot-pound per force. Force is in pound per force, and displacement is in feet. Okay, so we're still using the English metric system. So they ask you a question, well, they give you an example. Determine the work done if 150 pound per force is applied to an object until it moved a distance of 30 feet. Okay, so it started at 0 and it moved 30 feet. So its displacement is 30 feet. Okay, its displacement is 30 feet, and they give you a force of 150 pounds per force. So they want you to use the work is equal to force times displacement, where you plug in to solve for work 150 pounds per force times 30 feet, and your work is 4,500 foot-pound per force. Remember, work is not a property, it is a process. And if the displacement is 0, then you have not done any work. So in dealing with work in relation to energy transfer systems, it's important to distinguish between work done by a system on its surroundings and work done on a system by its surroundings. Work is done by the system. Work is done by the system when it's used to turn this turbine to generate electricity and in this turbine generator system. Work is done on the system when the pump is used to move this fluid from one location to another. So a positive value for work indicates work done by the system on its surrounding, and a negative value for work means that work is done on the system by its surroundings. So you need to understand positive W and negative W. Heat, like work, is also energy in transit. So work is a process, it's not a property. Heat, like work, is energy in transit. And so the transfer of energy as heat, however, occurs at the molecular level as a result of temperature differences. And so they use the symbol Q to denote heat. Sometimes you'll see this capital Q, sometimes you might see lowercase q. And for engineers, the British thermal unit, or BTU, is the unit for heat. Specifically, this is called 60-degree BTU because it's measured by a 1 degree temperature change from 59.5 to 60.5. So they're just justifying why it's a 60-degree BTU. And so just like work, the amount of heat transferred depends on the path. So earlier we talked about path independent, we talked about hugs. Here we're talking about work. The work is path dependent. Why? Because work has displacement in it. And if you wind up at the same part that you started from, you haven't done any work. So just like with work, the amount of heat transferred depends upon the path. It's not simply initial and final conditions of the system, like hugs. So also, as with work, it's important to distinguish between the heat added to the system from its surroundings and the heat removed from the system to its surroundings. So a positive value for heat indicates that heat is added to the system by its surroundings. And that's a contrast to a positive when energy is transferred from one system and negative when it's transferred to another system. So the symbol lowercase q is sometimes used to indicate that heat is added or removed from a system per unit mass. So the total heat, capital Q, added or removed is divided by mass. The term specific heat is not used for this Q, since specific heat is actually another variable. It's another parameter, it's another variable. So the quantity represented by Q is referred to simply as the heat transferred per unit mass. And the equation that sums this up is lowercase q is equal to capital Q over M, where lowercase q is the heat transferred per unit mass, and the units are BTM per pound mass. Capital Q, which is heat transferred, that's in BTU, and M, or mass, is in pound per mass. So they ask you the question, or they give you an example to determine the heat transfer per unit mass. If 1,500 BTUs are transferred to 40 pounds of water, and you say aforementioned equation, lowercase q is equal to capital Q over M, and then they substitute in 1,500, which is the heat transferred, divided by the mass, which was 40 pounds per mass of steam. So 1,500 BTU divided by 40 is 37.5 BTU per pound mass. So the best way To quantify the definition of heat is to consider the relationship between the amount of heat added or removed from the system and to change the temperature on that system. So everybody's familiar with, you know, when a substance is heated. We know that the temperature increases. When a substance is cooled, we know the temperature decreases. So the heat added to or removed from a substance produces a change in temperature, and we call that, well, they call that sensible heat. The unit of heat is defined in terms of changes in temperature. It's defined in changes in temperature. So another type of heat is latent heat, and this is the amount of heat added to or removed from a substance to cause a phase change. Okay. So if you want to go from solid to liquid or liquid to gas, there's a point in there, and you'll see down a diagram where you have to consider the amount of heat that's added or removed from the substance to change that phase. So certain times the solid to liquid, certain times you have increase in temperature, and sometimes you have molecular changes that have to happen so that you have a phase change. So sometimes it's just the substance is actually increasing in temperature. Sometimes it's not increasing in temperature because the phase is changing. Okay, so you can have the latent heat of fusion. So when heat is added and no temperature change occurs, that is what you're talking about. On that graph, you'll see the temperature is not changing, but the phase is. So first is the latent heat of fusion, and this is when you have a change of phase from like a solid to a liquid. That's the latent heat of fusion. The second is the latent heat of vaporization. And that's when you go from a liquid to a gas, or they say liquid to a vapor. Going from a liquid to a gas, that's the latent heat of vaporization. Going from solid to a liquid, that's the latent heat of fusion. So different substances are affected by different magnitudes based on how much heat is added. So given the amount of heat that is added to these different substances, the temperature is going to increase by different amounts. And that's why they come up with this equation. So the ratio of Q, or capital Q, added to or removed to a substance to the change in temperature, which is delta T, produced is called the heat capacity of a substance. And the heat capacity of a substance per unit mass is called the specific heat. It's called the specific heat of the substance. So the subscript P indicates that the heat capacity and the specific heat applied when you have heat added or removed at a constant pressure. Okay, so that lowercase p is talking about what happens at constant pressure. So C lowercase p or sub p, subscript p, and then lowercase c subscript p is that p is trying to tell you that this is happening at constant pressure. Okay, so capital CP is equal to Q over delta T, lowercase cp is equal to capital Q over M delta T, and CP is equal to Q over delta P. So the capital CP is the heat capacity, and that's in BTU per degree Fahrenheit. Lowercase cp is specific heat at constant pressure, BTU per pound mass degree Fahrenheit. And Q is in BTU, that's the heat transferred. Lowercase q is heat transferred per unit mass, which is BTU per pound mass. Mass is in pound mass, and the change in temperature is in Fahrenheit, is in degree Fahrenheit. So 1 pound of water raised to 1 degree Fahrenheit and 1 BTU of heat are added, and this applies that the specific heat, or the lowercase cp of water, is 1 BTU per pound mass degree Fahrenheit. And the lowercase cp of water is 1 BTU per pound mass degree Fahrenheit at 39.1 degrees Fahrenheit. So if you rearrange this equation, Q is equal to MC delta T. Q, capital Q, is equal to MC delta T, which is used to calculate the latent heat. By substituting mass flow rate in pound mass per hour, M, with this dot over it. For M, we obtain that Q with this dot over it is equal to M with this dot over it, Cp, lowercase c, delta T. And this equation is used to calculate heat transfer in BTU per hour, and is useful, and you'll see this equation become useful in later chapters. So how much heat is required to raise the temperature of 5 pounds of water from 50 to 150? Okay, initial temperature 50, final temperature 150. Where the specific heat of water is 1 BTU per pound mass per degree Fahrenheit. And so they use the equation Cp is equal to capital Q over M delta T. You see that they have gotten Q by itself by multiplying both sides by M delta T. So Q is equal to Cp M delta T. And then they plugged in the specific heat for water, which was 1. They plugged in the mass for water, which was 5 pounds per mass. And then that delta, of course, is final minus initial. So they subtracted 150 degrees Fahrenheit from 50 degrees Fahrenheit. So Q is equal to 1 times 5 times 100, and you wind up with a Q of 5 BTU. So from previous discussions on heat and work, you understand that there are similarities between heat and work. They're both transient phenomena. The system never possesses heat or work, but either or both occur on the system, and you understand that it undergoes a change in energy state. So heat and work are boundary phenomena. Heat and work are boundary phenomena. And both represent energy crossing the system's boundary. They are boundary phenomena. Entropy, or S, is a property of a substance as a pressure, temperature, volume, and enthalpy. So because entropy is a property, changes in entropy can be determined by knowing the initial and final conditions of a substance. And that's because it's a state function. That is because, unlike heat and work, it is a state function. It's path independent. So if you know the initial and final conditions of a substance, you can calculate entropy. So entropy quantifies the energy of a substance that is no longer available to perform useful work, because entropy tells us about the usefulness of an amount of heat that is transferred in performing work. So you have tables that include values of specific entropy, okay? So you saw in previous lectures where they have tables that have these standard values for S. So I already have tables with standard values for S. So entropy is referred to as the measure of the inability to do work for a given amount of heat transfer. The entropy is represented by the letter S and is defined by delta S. So delta S, and delta we're talking about the final and the initial and final conditions of a substance, is equal to delta Q over T absolute, T ABS. Okay. So delta S is the change in entropy, and that's in BTU per delta R. And delta R is Rankine. Delta Q is the amount of heat transferred to or from the system during the process, that's in BTUs. T abs is the absolute temperature at which the heat is transferred, and that is Rankine. Remember, we have two absolute systems. One is Rankine, the other is Kelvin, and that comes from the previous. So delta S is the change in specific entropy of a system during that same process, and that's in BTU per pound mass degree Rankine. And delta Q is the amount of heat transferred to or from a system during the process, and that's BTU per pound mass. So like enthalpy, entropy cannot be measured directly. Also like enthalpy, entropy of a substance is given with respect to some reference value. For example, specific entropy of water or steam comes from this reference that specific entropy of water is 0 at 32 degrees Fahrenheit. The fact that absolute value of specific entropy is unknown is a problem because we use the change in entropy and not the absolute value. It's the change for delta S. So energy and power. So various forms of energy involved in energy transfer systems, such as potential energy, kinetic, internal, heating energy, work, and heat. They are measured in numerous basic units. So in general, we have three types of measure for energy: mechanical units, such as foot-pound per force; thermal units, such as BTUs; and electrical units, such as watt-seconds. In the MKS and CGS systems, the mechanical units of energy is the joule and the erg. So MKS is meter, kilogram, second, or centimeter, gram, second systems. These are SI systems. And they're saying that mechanical energy is in joules in these SI systems or metric systems. That's based on a meter, kilogram, second being the standards, or a centimeter, gram, second being the standards. Okay, so they're all of this is referring to like not an English system, but the international system of the SI system. Okay, so they're going in between two systems, English and metric. English. So although the units of various forms of energy are different, they are equivalent. Meaning there's some conversion factor between the metric or SI system and the British or English system. There is some conversion factor, so they are equivalent. So some of the most important experiments are conducted by Joule, 1843, who showed quantitatively that there was a direct correspondence between mechanical and thermal energy. And his experiments, he showed that 1 kilocalorie, this was his conversion factor, is equal to 4,186 joules, 1 kilocalorie. So he's trying to still go between these units using a conversion factor. Okay, so they fleshed it out in this sentence, but this is a conversion. Okay, and so these same experiments were performed using the English system unit, show that 1 BTU is equal to 778.3 foot-pound per force. That's another conversion factor. And these experiments established the equivalence of mechanical and thermal energy. Of experiments established the equivalence of electrical with both mechanical and thermal energy. Okay, so in order to look at the equivalence of these various forms of energy, of course, there was some lab work that was done, and he came up with these conversion factors to go between the different systems, to go between metric or SI and British or English. Okay. So for engineering, these equivalents are expressed by the following, and so they give you a list of conversion factors. They give you a list of conversion factors. So 1 foot-pound per force is equal to 1.286 times 10 to the minus third BTU is also equal to 3.766 times 10 to the minus 7 kilowatt hour. Kilowatt hour. A BTU is equal to 778.3 foot-pound per force and it's also equal to 2.928 times 10 to the minus 4 kilowatt hour. And a kilowatt hour is also equal to 3.413 times 10 to the third BTU. And that's equal to 2.655 times 10 to the 6 foot-pound per force. So they're showing you, just like you guys understood that there's 12 inches in a foot, they're also showing you that in between these different units or forms of energy, there's also a conversion factor. Okay. And then there's an additional unit of energy that is encountered with these engineering applications. Okay, so and that is horsepower. It's a mechanical unit of energy. So 1 horsepower is equal to 1.98 times 10 to the 6 foot-pound per force. So this is 1 horsepower hour is equal to 1.98 times 10 to the 6 foot-pound per force. So this allows you to convert between the various English system units for the various forms of energy. So most computations involving energy of a working fluid in the energy transfer system are performed in BTUs. Forms of mechanical energy, such as potential energy, kinetic energy, and mechanical work, and other forms of energy, such as EV energy, are usually given in foot-pounds per force. And they're showing you a conversion factor for BTU. So 1 BTU is 778.3 foot-pounds per force. So this conversion factor is often used. In fact, the constant called the mechanical equivalent of heat is denoted by this capital J, and J is Joule's constant. J is Joule's constant. Okay, and Joule is equal to 778 foot-pound per force per BTU. Power is the time rate of doing work. Power is the time rate of doing work. It's equivalent of a rate of energy transfer. And so power has units of energy per unit time. And so that's what you see when you start talking about power. Okay. That's what you see when you start talking about power. In English, it's mechanical units of power are foot-pounds per force per second per hour. Okay. So every time they have that per second, every time they have that per hour, we understand that that is a rate. Every time they have it per second, every time they have it per hour, we understand that that is a rate. And horsepower. So every time we have that divided by second or divided by hour, we're talking about a rate. The thermal units of power are British thermal units or BTUs per hour, and the electrical units are watts or kilowatts. And so then they're going to express the equivalence and by giving you these conversion factors. So foot-pound per force per second is equal to 4.6263 BTU per hour, which is equal to 1.36 times 10 to the minus third kilowatts. 1 BTU per hour is equal to 0.2162 foot-pound per second, which is equal to 2.931 times 10 to the minus 4 kilowatt. And a kilowatt is equal to 3.413 times 10 to the third BTU per hour, which is equal to 737.6 foot-pound per force per second. And horsepower is related to foot-pound force per second. So 1 horsepower is 550 foot-pound per force per second. Okay, and this helps you convert between the two systems, the English system and the CGS MKS systems. So here's another summary. I'll give you guys an opportunity to put any conversion factors and equations here. So the next thing we're gonna talk about are thermodynamic systems and processes. Remember earlier we said that work is a process. It's not a property, it is a process. And so we're going to describe the different types of thermodynamic systems. So what's an isolated system? What's a closed system? What's an open system? And then of course define these terms concerning the system, which is thermodynamic surroundings, thermodynamic equilibrium, control volume, and what is steady state. And then we're going to describe the terms, thermodynamic process, cyclic process, reversible process, irreversible process, adiabatic process, isentropic, throttling, and polytropic process. And so, when I was in graduate school, the reason that these were important is because they told me what I didn't have to do. So they would string a lot of these terms together so that I would know what not to do partial derivatives on. So these thermodynamic systems and surroundings, thermodynamics is a study of various systems. So a system in thermodynamics is nothing more than a collection of matter that is being studied. A system could be water within the side of a heat exchanger, fluid inside of the length of a pipe, lubricating oil system for an engine is also a system. And so determining the boundary to solve the thermodynamic problem for a system depends on what information is known about the system and what question can be asked about the system. So a system could be water inside of a heat exchanger, fluid inside a liquid pipe, lubricating oil inside of a diesel. Those can be considered systems. And so as chemists, the way we mimic what is happening to try to understand a system is we do something called bomb calorimetry. And it helps us understand what happens in a system and what happens in the surroundings. So experiment-wise, we use bomb calorimetry. And for me, it kind of looks like, you guys like make ice cream. You got all the ingredients inside of a container, and then outside you got like rock salt and ice. So for us, that's kind of what bomb calorimetry kind of looks like. And that's how we study a system, which is everything inside of all the ingredients inside, and then the ice and rock salt. We would call that the surroundings, and we would see how what happens in the system impacts the surroundings, or what happens in the surroundings impacts the system. Okay, and so that's how we study it. So everything external to the system is called the thermodynamic surroundings, right? So for us, the surroundings would be like the rock salt and the ice. Those would be like the surroundings. The system is separated from the surroundings, and we would call that the boundary. So that bucket that all this stuff to make the ice creams in, we would call that the boundary. Okay. In bomb calorimetry, whatever we have inside of the bucket or cup or container, that's our boundary. And so the boundaries, they can either be fixed or they can be movable. In many cases, thermodynamic analysis must be made of a device such as a heat exchanger that involves flow of mass into and out of the device. Flow of mass into and out of the device. And a procedure that is followed is such to the analysis is to specify a control surface, such as the heat exchanger tube walls. Mass, as well as heat and work, and even momentum flow across the control system. Mass, as well as heat and work. And so for us, if you go back to like the way you see people like making ice cream, we know that heat is going to flow from the surroundings into the system, into the surroundings. There's going to be heat transfer, and that's why you're going to wind up with something frozen. So thermodynamic systems are systems, they're classified as isolated, closed, or open based on the possible transfer of mass and energy across the boundaries. An isolated system is one that is not influenced in any way by its surroundings. This means that no energy in the form of heat or work crosses that boundary. And in addition, no mass may cross that boundary. Okay. Mass may cross that boundary. A thermodynamic system is defined as a quantity of matter, a fixed mass, and identity upon which attention is focused for the study. A closed system has no transfer of mass with its surroundings, but may have transfer of energy. So the system that I was just talking about, like making ice cream, that is a closed system. So you're not gonna let all the ingredients flow out to where the rock salt ice are. So that would be a closed system. So a so an open system is one where you have transfer of both mass and energy with its surroundings. Open system is you can transfer. So if there's some sort of hole in a container or something like that, and of course, those ingredients flow out. And also heat and stuff like that is transferred between the systems, so that would be open. Like all the ingredients kind of like spill out. So thermodynamic is equilibrium when the system's in equilibrium with regard to all changes in state. We call this thermodynamic equilibrium. For example, gas that comprises a system is in thermal equilibrium, and so the temperature is the same throughout the system. The way I kind of like to think about this is whenever you like have like you're heating or cooling your house and you have everything at the same temperature throughout your house, then that would be like equilibrium, right? Because you got to take outside air and you got to take inside air, and then the systems like exchange it, and it comes to like a constant temperature. It comes to like a constant temperature. It's more complex than that, but I'm just trying to describe air flowing in and out and temperature being the same throughout your house. That's probably the best way that I can think of talking about with gas, which is air. Constant volume is a fixed region in a space chosen for a study of mass and energy balances for a flowing system. So the boundary of control volume may be real or imaginary. It may be real or imaginary. And so here we go with this esoteric shared language, because people can't imagine an imaginary. So that's the best way that we can think about what happens when we kind of like graph out this control volume. Okay. So the control surface is the boundary of the control volume. The control surface is the boundary of the control volume. Okay. So we think of spaces where we do these thermodynamic studies. Spaces where we look at these systems, and we have to like define these spaces. And that's why they're saying these spaces, they can be real or imaginary. Okay, that's why they're saying that these spaces, they can be real or imaginary. And like I said, as scientists, we have this esoteric shared language. I'm trying to think of, and so the way that you usually see this is something that is graphically represented. The way that you see this is something that is graphically represented. So steady state is that circumstance where there is no accumulation of mass or energy within that control volume. Steady state is where there's no accumulation of mass or energy within that control volume. That's what we're talking about, that fixed region. You don't have an accumulation of mass or energy. And properties at any point. So within that, the properties in that system are independent of time. So this is just, for me, is saying that you have volume. Okay, and you're just talking about that one volume. You have a boundary for that. Okay, so you got a line on that graph. And you're not thinking about time. I don't know if you guys have ever seen, but there are even like different ultrasounds that you. And so the one that you can get where you can see like the entire surface of the child, the variable is time. So those are, I think, 4-dimensional. Those are the more expensive ultrasounds. So you can see those flat pictures that people typically get with an ultrasound, but then they can actually record like videos if they do 4D because the other dimension is time. So they're talking about now not having another dimension on the graph. So they're saying like you won't have all of these extra dimensions on the graph. So that because it's independent of time. A thermodynamic process, whenever one or more properties of a system change, a change in the state of the system occurs. The path of succession of states through which the system passes is called a thermodynamic process. And a process, one process is increasing temperature of a fluid while maintaining constant pressure. And so for us, you know, we just take physical chemistry 1, 2, or 3, and then of course in graduate school, we wanted to know what kind of process was going on. So we knew what we didn't have to do, what we didn't have to do, what we could consider was happening at constant temperature or constant pressure. So thermodynamic processes will be discussed, you know, more later. Then you have a cyclic process, right? And this is when a system in a given initial state goes through a number of different changes of state and finally returns to its initial value. So the system undergoes this cyclic process. Therefore, all the properties have the same value that they had at the beginning. So steam water circulates through a closed cooling loop and undergoes a cycle. Steam circulates through a closed cooling loop and undergoes a cycle. The reversible process for a system is a process that once it's taken place, it can be reversed. And in doing so, it leaves no change on either system. Okay. In other words, the system and surroundings are returned to their original states or conditions. In reality, there are no like truly reversible processes. However, for analysis purposes, we use reversible to make it just makes it easier. And so we're able to determine theoretical efficiency. So the reversible process is important. The reversible process is important. Like I said, we have this esoteric shared language or way that we like to think about processes in order to simplify what we have to do mathematically. So although a reversible process can be approximated, it can never be matched by a real process. So one way to make real processes approximate what a reversible process is to carry the process out in a series of small infinitesimal steps. And for me, when I think about anything that's infinitesimal, I'm thinking about calculus. I'm thinking about integration. I'm thinking about integration. For example, heat transfer can be considered reversible if it occurs due to small temperature difference between the system and the surroundings. For example, transferring heat across temperature difference of 0.1 0.00001 degree Fahrenheit appears to be more reversible than transferring heat across, processes where you have a temperature difference of 100 degrees Fahrenheit. So the heating or cooling system in a number of infinitesimally small steps, we can approximate what a reversible process is. If you look at the entire system, then of course you understand that you're going to lose some of what you initially put in. So for example, if you think about cooling your home, even though you have that freon, eventually you're going to have to add some to it. Okay, so that system is not completely reversible. Okay? You're going to lose some of it. So, eventually you're going to have to add some freon back to that system when you think about cooling your home or refrigeration. So although it's not practical for a real process, the method is beneficial for thermodynamic studies since rate at which processes occurs is not important. Okay. An irreversible process is a process that cannot return both the system and surrounding to their original conditions. So the system and the surroundings wouldn't return to their initial or original conditions if the process was reversed. For example, an automobile engine doesn't give back the fuel when you drive up the hill. And even more so than that, when they think about imaginary versus real, all of that fuel, we can't say every single bit of that fuel is converted to work. Some of it is lost in different ways in terms of the way you think about cars. If not, then of course you would have a car that was just so perfect that it would break certain laws of thermodynamics. So there are many factors that make a process irreversible. Four of the most common causes of irreversibility is friction, unrestrained expansion of a fluid, heat transfer through this finite temperature difference, and mixing of different substances. So that happens in cars, that happens in refrigeration, that happens in the freon that you use to heat, to cool your home. Okay. The adiabatic process is the one where you have no heat transfer into or out of the system, and the system is considered to be perfectly insulated. Of course, we understand that is a little bit more theoretical than what happens in real life. We don't have like perfectly insulated homes. We don't. We can get pretty close to like really good insulation, but it's just not. Isentropic processes are ones where entropy of the fluid remains constant. Isentropic is the entropy of the fluid remains constant. And this will be true if the process goes through an irreversible, through reversible or adiabatic type changes. So an isentropic process can also be called constant entropy process, a constant entropy process. Polytropic is when the gas undergoes a reversible process, which heat transfer, which the heat is transferred. Okay, process is frequently taking place in a manner of this plot. So we have log of pressure versus the log of volume, and this is a straight line, and that's why PV is equal to a constant. Okay, so PV is equal to a constant because you have the straight line. We start talking about polytropic processes. So an example of a polytropic process is the expansion of combustion gases in the cylinder of a water-cooled reciprocating engine. That is a polytropic process. The throttling process is defined as a process where there's no change in enthalpy. So we have entropy remaining constant, no heat transfer. Now we're talking about no change in enthalpy from one state to another. Okay, so that's why they use that H to 1 is equal to H to 2. No work is done, work is equal to 0. And the process is also adiabatic. So Q is equal to 0. So to better understand this theory of ideal throttling process, we have to compare what you observe with these aforementioned theoretical assumptions. So the throttling process is of an ideal gas flowing through a valve in mid position. We have P in is greater than P out. We have P in is greater than P out. Vel in is smaller than vel out, where P is the pressure and vel is the velocity. And this confirms the theory that H in is equal to H out. And remember that lowercase h, you saw it when we start talking about internal energy. We start talking about enthalpy and how it relates to internal energy. So H is equal to U times PV, where V is the specific volume. So if pressure decreases, then the specific volume has to increase. Pressure decreases, the specific volume has to increase if the enthalpy is to remain constant. Because mass flow is constant, the change in specific volume is observed as an increase in gas velocity. And so they're trying to say that throttling is where you have no change in enthalpy. The theory also states that work is equal to 0. And our observations again confirm that this is true. As clearly as no work has been done by the throttling process. So finally, the theory, it tells you that ideal throttling is adiabatic. And again, this is not something that you can clearly prove since real throttling process is not ideal. And you're going to have some heat that is transferred. Okay. So, you know, what happens in reality, you guys understand what happens with cars. Everything is not perfect. You don't get your fill and then just get 100% work out of it. You understand when you're using, you know, heating or cooling unit for your home, that eventually you're gonna have to add some freon back. And that's because those systems are not perfect. That's not exactly how it happens in the real world. So again, you have the summary and all the definitions here. So take some time and make some notes here.